I hope you enjoy it. And if you are not a member, I encourage you to join. It's a great club. We just introduced the new board and the officers and directors. I'm the president. I'm Jessica, and we have our vice president is Bill. He's on here. We have our secretary, Anthony Barrero. We're very lucky to have him back on the board. We have treasurer Jim Burke. We have directors Douglas Smith, Liz Triggs, PJ Cabrera, Evan Ryder, Mike Wingrath, and Thomas Perfumo, and that is your board for this year. And I would just like to add that all of our board meetings are open to members. If you would like to attend online, please do so. We are open to ideas and volunteers. We have some updates about our star parties. Mount Tam is still on hold based on the California state parks. They are not allowing any reservations of any kind. As soon as they are, we will submit our application, and we are going to try and add 2 star parties a month. Hopefully we will have some of them this year. The city star parties are also on hold, but we do encourage all of our members to go out and observe the night sky. If you want to get together with other members, we encourage that. Just be safe and enjoy looking up. As some of you heard earlier, Bill, our vice president, is working on a new offering. It's an observing basics class. He is working out the details and how exactly that is going to happen. It is all online, and as we know more about it, we will let you know. And then our loaning program, which some of you heard earlier, is currently on hold. But if you would like to get in the queue to reserve a telescope, you can email the telescope@sfa-astronomy.org and get on the list. And Douglas is always available to answer questions about the telescope program, what telescopes we have, and things like that. So that is all for the president's notes, and I am passing it over to Linda, who I will now unmute. Linda, you have to unmute yourself.
Can you unmute her, Jessica?
I can only ask to unmute her.
Ah.
Okay, there I am. Okay, I was looking in the wrong spot. At any rate, the next 2-month speakers, February 17th, how galaxies are influenced by the largest structures in the universe. This is by Dr. Mehmet Alpazlan. He's a former research fellow at NASA Ames and from NYU's Center for Cosmology and Particle Physics. When viewed at the largest scales, the distribution of galaxies in the universe resembles a complex, tangled web, an interconnected network of filaments and vast empty voids. We will learn about the advances in telescope instrumentation to help map out the network of the universe. On March 17th, celebrating Stephen Hawking, how black holes are not quite black. This is given by a much respected and admired Bay Area astronomer, teacher, Andrew Fracknoy. He's the emeritus chair of the astronomy department at Foothill College. And he gives lectures in many, many places and has many classes that many people have attended. So he's very much admired. Scientists and science enthusiasts are still mourning the passing of Stephen Hawking. Our speaker will briefly summarize Hawking's life and importance and about his scientific work. He'll focus on Hawking's work on the big and heavy and the small and light. He says, prepare to be boggled. So those are February and March's lectures. Tonight, I'm pleased that we have as our speaker, Sunil Simha. He attained his bachelor and master's degree in physics from the Indian Institute of Technology in Madras in Chennai, India. He was inspired to pursue astronomy and physics when he qualified to attend an astronomy Olympiad training workshop in the 12th grade. I'm so pleased that that happened. In college, he participated actively in the university's astronomy club. He organized and gave talks and also conducted public observing sessions. After working on a research project on quasar absorption line studies during his summer at the Inter-University Center for Astronomy and Astrophysics in Pune, India, he decided to pursue studies in astronomy. Following an opportunity to work with Professor Javier Prochaska at UC Santa Cruz during a summer internship abroad, he applied to UCSC's PhD program in 2018. Since then, he's been working on using fast radio bursts as cosmological probes under Professor Prochaska's guidance as part of the CRAFT, capital C-R-A-F-T, and this other F4 team. He's also involved in the red side detector upgrade of the LRIS, which is the low resolution imaging spectrometer on board the Keck telescope in Mauna Kea, under the leadership of Professor Constant Rakosi at UC Santa Cruz. We very much look forward to hearing your talk tonight and welcome you very, very much. Thank you for joining us, Sunil Simha. Thank you. He will be speaking about mapping the missing matter in our universe. That's the title of his presentation tonight. Thank you so much.
Thanks for having me. That was a wonderful introduction. I'll start by sharing my screen.
I'm pleased that you started early and did a lot of what we like to do, public astronomy and showing people the sky.
Oh yeah, that was, I think, the best time of my life, undergrad years. Okay, so can everyone see my screen?
Mm-hmm. Yes. Yeah.
Okay. Well, thanks for having me here, and thank you everyone for being here to listen to me talk about my work that I've been doing as part of the CRAFT and F to the fourth collaborations. So today I'll be speaking on how to map the missing matter in our universe. The outline of the talk will be a bit as follows. So first, I will give you a brief introduction of the missing baryon problem, followed by an introduction of what fast radio bursts are. And then finally, I will talk about my latest work, the latest work that I led. And here are some of the members that were instrumental in the success of this work. So we have Joseph Burchett, Xavier Prochaska, Oscar Alec, all of them from UC Astronomy, and Jay Chittadi, who's a graduate student, and he's also part of the group. So this will be mostly on the paper here that we recently published. It's called Disentangling the Cosmic Web Towards FRB 190608. So like any cosmological talk, we begin with an introduction of the Big Bang, brief history of time, if you will. So you know the song, the whole universe was in a hot, dense state, yada, yada, yada. So something happened and we had the universe expanding and it cooled down and matter structure formed and we got stars, galaxies, and our own Milky Way. So 13.7 billion years later, we are here and we're looking back at the universe. So the further away we look, the further back in time we're seeing because light has a finite speed and it takes time for information to reach us from distant parts of the universe. So if you look far enough, you will see the cosmic microwave background. What this is you can think of it as a snapshot of the baby universe when it was just 300,000 years old. The cosmic microwave background is radiation that is extremely uniform and it's coming from all parts of the sky. It is called the microwave background because it's predominantly in the microwave regime. This is what scientists call black body radiation. Now, what does that mean? It means that it behaves exactly like how a hot body would emit light. So if you had a piece of glowing coal or a piece of hot iron, the spectrum of the light that would come from it would be very similar to what the cosmic microwave background spectrum looks like. What you see over here, however, in this picture is the inhomogeneities in the temperature of the microwave background. So the microwave background has a temperature of 2.7 Kelvin. That sounds really cold, but it's simply the fact of redshifting from the early universe. But you see fluctuations of this temperature, and these fluctuations are really tiny. So they're like 1 part in 10 to the 5 or 100,000. So they're really, really tiny. But they give you a clue of what the universe is made of. So if you were to analyze the statistics of these fluctuations, then you can infer how much what the universe is made of and how much of that stuff exists in the universe. So we know from studying this data that about 68% of the universe is made of dark energy, and about 27% of the universe is made of dark matter, and the remaining 5% or so is made of baryonic matter or regular matter. There is also a very, very tiny quantity of light and relativistic particles like neutrinos, but their contribution to the total budget is so small that we're going to ignore that. So if you notice, about 95% of the universe is made of stuff that we have no idea what they are. So dark energy is some sort of mysterious force that seems to be pushing everything away. And dark matter behaves exactly like regular matter when it comes to gravity. That means it pulls things together, but it does not interact with matter in any other way. That is to say, we don't see any sort of electromagnetic or strong or weak interactions. So this is completely invisible to us. And therefore we have no idea what it is and what it's made of, basically. So if you were to take these fluctuations on the CMB and you were to allow it to evolve over time, so what do these fluctuations represent? They're essentially density fluctuations. So there are regions in the universe that were slightly more dense than the other parts. So if you allowed gravity to take over and you gave it 13.7 billion years, what would the universe look like? According to simulations, it would look something like the image on the right side here. So this is from the Millennium simulation, and it's a cosmological simulation on a large scale. What you see here is basically dark matter. These colors are not real. These colors only represent a density of dark matter in the universe. You might remember from the previous slide that the dark matter corresponded to about 25% of the universe. So it's a very dominant entity in a formational structure. So all the regular matter basically follows the same density matter distribution as the dark matter itself. So you have these structures called halos over here that are shown in bright yellow, and you have filamentary structures, and you also have voids out there in space. So these are regions of low dark energy density or matter density in general. And all your regular matter, gas, galaxies, everything is distributed along these filamentary structures. And this is called the cosmic web. So I told you that we know from the CMB that the universe is made of roughly 5% of regular matter. So if we wanted to verify this, what would one do? One would perform a Baryon Census. So they would look at every single object and try to count how many baryons are there in these objects and gas, basically, and say and compare it against the predicted amount from the CMB. As of 2012, this is the summary of such studies by Shull, Schmidt, and Danford. So we knew that about 20% of regular matter exists in collapsed form. This means it makes up stars and galaxies, dead stars, all kinds of stars, and the CGM, or the circumgalactic medium, so the matter that surrounds galaxies, this is mostly gas. The intercluster medium, ICM, so this is gas that is found in galaxy clusters. So if you have a bunch of galaxies that are gravitationally bound and are within one of these dark matter halos, there's a good chance that outside these galaxies, there's going to be a whole lot of gas, and that is called the intercluster medium. And also there is cold gas that's just floating around, and that comes from 21 centimeter survey observations. And about 20 to 30% of gas exists in the form of cold Lyman alpha forests. So these are just neutral or hydrogen gas that are just floating around, and these get detected in absorption from background light. And about another 25% exists as warm hot gas, and these have been detected via Lyman alpha absorption or warm hot intergalactic medium oxygen 6 emission. So this gas is really hot, and therefore many of the species that live in it are really ionized, so we can detect them in the form of atomic or ionic absorption spectra, and oxygen 6 is one such popular probe. And using that, we are able to say, okay, about 25% of baryons exist in this state. And so that still leaves about 29% or 30% of matter that is not really accounted for, and it's considered missing. So that is a problem. This might be a misunderstanding of the CMB, or it just might be some sort of deficiency in our observational techniques. We're clearly not accounting for something here. So where is the missing matter? If you run simulations of matter, of cosmological simulations with regular matter in them, you will realize that a whole lot of gas or just hydrogen and helium, for instance, are located along these filamentary structures that I mentioned earlier. And not only are these structures really diffused, they're also fully ionized. And that makes it really hard for us to detect them, because if these gas particles or atoms were there in atomic state as opposed to being fully ionized, we would detect them as absorption lines in distant quasar spectra, and we don't do that because they're fully ionized. And so the more physics savvy among you might think, hold on, if they're fully ionized and if there's a background source, they should still interact with it, because background radiation is just electromagnetic radiation, and ionized gas is still charged particles, so they must interact with it in some way. And that is true. They do interact, and we actually can detect it statistically through something called the Sunyaev-Zildjić effect. So if you were to look at the cosmic microwave background through these filaments, you would notice a very, very tiny distortion in the spectrum of the CMB in that direction where the filaments exist. So a bunch of scientists, or I think 2 groups of scientists, published their findings in 2017 about this, where they took a whole lot of galaxy pairs and where they suspected these pairs to be connected by filamentary structures, and they stacked them together, and they found the distortion signal, and which confirmed that there was all this diffuse gas sitting over there. But because it was extremely diffuse, it was really hard to detect directly. So that begs the question, is there a more direct approach? Sure, we have solved the missing baryon problem. All the matter has been accounted for, but it would be nice if we could directly see all of this matter out there. And this is where FRB comes. Before I talk about how FRBs can help us, let me give you a brief introduction of what FRBs are. So FRBs are, they are transient events. These are, FRB stands for fast radio bursts. So these are, as the name suggests, they're radio transient events. I'm sorry, I think I forgot to remove a transition. But anyway, these fast radio bursts are millisecond duration. So they only last a couple milliseconds. And we have no known optical counterpart to them. And we know that a whole lot of these are coming from outside our galaxy, and they're extremely bright. And they occur at an all-sky rate of roughly 4,000 per day. And the way FRBs were discovered was totally by chance. So Duncan Lorimer, a professor, had given his undergraduate student, David Narkovic, a project to go through the park's Pulsar survey archives and essentially find out, or find if there were any pulsars in there that were not accounted for. What David found was not pulsars, but, well, I mean, I guess he did find pulsars, but he also found some other objects that were peculiar in there. And initially, it was thought that this was probably some sort of instrument error, but after careful analysis, it turned out to be an actual object, astrophysical object. And so David and Duncan published their findings in 2007. Note that the detection had actually happened in 2001, however. So what was David looking for in these archives? So he was looking for a class of objects called pulsars. Pulsars are neutron stars that are emitting light from their magnetic poles. And on the right over here, you see an animation of what that might look like. The neutron stars are what you get after really massive stars, something like 10 solar mass stars, die in a supernova, and their core collapses into this degenerate matter of matter. So you have something that is really, really massive and really dense, because neutron stars are typically around 1.4 solar masses, or sometimes a bit higher. And they are about as big as a city. So their diameter is something like 10 miles. So they're really tiny, but they're extremely dense. And they are also rotating really, really fast. So typical neutron star or pulsar rotation rates are something like 60 RPM, which means they're going around their own axis once every second. Sometimes they go even faster, nearly 1,000 times faster. The Crab pulsar is one of those objects, so that it has a neutron star that is going, I think, once every 3 milliseconds or something like that. So really, really fast. And because these are extreme objects, they also come with extreme magnetic fields. So you can think of these magnetic fields being millions of times stronger than the Earth's magnetic field. And at that level, it is capable of producing radiation from its poles. So they have their own magnetic north and south poles, and they're producing radiation from it. Most of this radiation is in radio waves, although they do emit other forms of radiation as well. And so because the rotation axes of these neutron stars are misaligned with their magnetic axis, just like the Earth, whenever a pulse, we see them as pulses of light that continuously repeat. So from Earth, they basically look like sirens that are going round and round, and they're repeating every now and then. So these are very regular repeaters. And since it's radio light that is coming from these pulsars, and it's traveling through plasma before it reaches us, this light gets dispersed. Dispersion of light is a very common phenomenon that many of you have seen before. So whenever you have white light passing through a prism, it comes out in all of its different constituent colors. This is because light travels at different speeds based on its frequencies within the prism itself. And the same thing happens to radio light coming from pulsars towards us. Because space is not empty and it contains a whole lot of gas and plasma, the speed of light depends on the frequency of light inside the plasma. And so higher frequency radiation travels towards us much faster than low frequencies. And pulsar light therefore has a very characteristic shape when you plot the pulse arrival time as a function of frequency. So, the other way around. Frequency as a function of pulse arrival time. So this is the observation made by Lorimer, David and Lorimer from the Pulsar archives. So what you can see over here is a signal that they found in the archive. So the higher frequency radiation pulse is coming in earlier, this is the time of arrival, than the lower frequency. And it has this very characteristic shape that can only, that can be explained by plasma dispersion. So pulsars basically look like, pulsar pulses look like this, but they repeat on a regular basis, once every second or so. Fast radio bursts, on the other hand, don't really repeat all that much. Even if they do, they're very irregular, and sometimes they take days, if not months, to repeat. So this was something peculiar that they detected. So it was a one-off event, and this was never seen before. And if you look at how far apart these two frequencies were when they arrived, so the difference in the time of arrival, that gives you an idea of how much matter the light traveled through. And this is quantized by something called the dispersion measure. And what they noticed was that FRB dispersion measures are much, much higher than pulsar dispersion measures. So this meant that this FRB light was going through a whole lot more material. In fact, so much so that this much matter could not just exist within our own galaxy, and therefore these light sources must be outside our galaxy. And that's how they were inferred to be extragalactic. So here's a neat movie I found that shows you what the dispersion measure of an FRB means. So you have a galaxy and an FRB happens, so you have different wavelengths or frequencies of light traveling towards us, and as they travel within matter, they get dispersed. So the purple light, the higher frequency, travels faster than the red light, lower frequency. Note that all of this light is neither purple or red, it's just radio waves, but we're just using it for visual representation here. And finally, it reaches us, it reaches the solar system, and it gets captured through one of the radio telescopes that we have. This is the ASCAP instrument in Australia. And the light gets processed, and we see this dispersion effect. And the pulse is detected from the FRB. So the more matter there exists, the more it gets dispersed. So FRB can really trace out ionized matter through this property of dispersion measure. So this is great news. So I previously said that there was a whole lot of ionized gas, which was really diffuse and it was hard to detect because there were, it was just really diffuse. FRBs offer a way to detect this ionized gas. And that's great. We can now start using FRBs as probes of cosmology then. Before I go on to talk about my project, I must address the question of how are FRBs produced. We don't really know exactly, but we have a hunch that it is probably produced by magnetars. And what are magnetars? Magnetars are essentially pulsars, but they have magnetic fields that are about 100 to 1,000 times stronger than regular pulsars. So these are thought to be really young pulsars, and they usually have weird glitchy events where they produce a lot of emission flight. We think they are starquakes, so something on the surface or star happening, and that is producing this light, but we're not totally sure that if this is the cause for all the FRBs. We think so because we think it might be because we as in astronomers detected a FRB-like event coming from a galactic magnetar, something from our own Milky Way. This was SGR 1935 plus 2154. And this FRB-like burst was discovered on 28 April last year. Although the burst was fainter than the faintest FRB that was discovered so far, we think that at least some of the FRB events must be produced by magnetar sources, if not all. So that's that. Still stay tuned to find out how FRBs are produced. But for now, we can still use FRBs to do a whole lot of cool science. And now I'm going to talk about my project. And this was on FRB 190608. So the naming convention is year, month, and date. And this is the full name, 2019-06 June, 8th of June. And A stands for which the order in which it was discovered. So this was the first FRB discovered on that date, so A. And this event occurred in the spiral arm of a nearby galaxy, nearby being relative. This galaxy was 1.5 billion light years away. This is close in cosmological scales. And this is a picture of that spiral galaxy that we got using the Hubble telescope. And the FRB came from this red circle over here. Notice how it lines up very nicely with this clump of gas over here. And this is a UV image. So that means it whatever you're seeing here is tracing out star formation activity. So this FRB was associated with this star-forming clump over there, which is nice. It's an interesting discovery. This host galaxy was already present in the SDSS optical database. So if you're not familiar with the SDSS, it's a very useful and nifty public database of images and spectroscopic information of a really large patch in the northern hemisphere. And so if you've never used it before, I highly encourage people to go and check it out. you might find some really good images, or if not that, just good data overall. So this was really lucky for us because now we had information about a whole bunch of galaxies right in front of the FRB host, and we could then start studying what the matter distribution looked like using the FRB dispersion measure. So what does the information in the SDSS database tell us? Before I talk about that, it's good to get a mental picture of what the system that we're looking at. So the FRB host exists at some distance. The FRB event happened, and the light from the FRB traveled towards us to the Milky Way. And so there is a whole lot of stuff in between us and the FRB. And from SDSS, from the spectroscopic data in the SDSS, we are able to tell the 3D positions of all of these galaxies, of these foreground galaxies. And we can also infer how massive each of these galaxies are based on how bright they are in every band. So that is done using some modeling, of course, but it's a fairly robust estimate, although with some uncertainty of how massive these galaxies are. And we can also then infer how much ionized gas there surrounds these galaxies based on how massive they are. So there is a very good relation that maps stellar mass estimates to halo mass estimates. And that's what we used to estimate how much gas exists surrounding these galaxies. So we can now start performing an accounting of the dispersion measure. So since dispersion measure is an additive quantity, the more matter travels through, the more it becomes. Through some careful modeling and analysis, we were able to infer that about 33% of the dispersion measure is coming from the host galaxy and the gas surrounding it. And about 33% is coming from our own Milky Way. And looking at the data from SDSS, we were able to tell about 5 to 8% of the dispersion measure comes from the gas that surrounds these galaxies in between us. So where is the rest of the dispersion measure coming from? Well, it must come from the cosmic web, the diffuse gas, that is, specifically. But there is a problem. Right, so there is a problem. This diffuse gas is really invisible, and to estimate its contribution to the dispersion measure would be slightly difficult because we don't really know how much of it exists and where it exactly is. So we need to first model the dispersion, the cosmic web itself. So two members of the team, Joe Burchett and Oscar Elek, they had previously invented this really wonderful technique that helps us do exactly this. So they were inspired by something called a slime mold. So this is a very simple organism. It's essentially a group of cells that behave collectively. It's fungi. It's a form of fungi, I guess. So if you take a slime mold and you leave it on a petri dish with some food particles, say, then the slime mold tries to search for these particles. So it basically sends out tendrils to search for these food particles, and once it finds a particle, then it collectively moves towards it, as you can see here in the GIF. And so it continues doing this until it finds all the food particles, and in the end, you're left with a network that connects all the food particles together, and that is basically the networking structure that you see over here. So what Oscar and Joe did was that they took a bunch of galaxies. So they asked the question, well, can we use the slime mold as an inspiration to trace out the cosmic web filament from the galaxies that we observe in the universe? And the answer to that turned out to be yes, we can totally do that. So that's what they did. They invented this Monte Carlo Phi-Sarum machine, or the MCPM, which simulates the movement of these slime mold particles. So the data that you feed to it is the 3D locations of a whole lot of galaxies. And you also tell how massive each of these galaxies are. And when you feed them and you turn on the simulation, the slime mold particles go through their process. They try to find out all the food particles, which in this case are galaxies, and they connect them via a network-like structure. And that network-like structure, in the end, is what you can use as a density estimator for the diffuse gas or the filaments that are present in the cosmic web. So with this technique applied on the SDSS galaxies in our FRB field, we were able to produce this beautiful 3D model of the cosmic web filaments. So what you see over here in red, this red line over here at the center, is the FRB sightline, and the FRB is here towards the right side, and we are here towards the left. So it's coming through this cosmic web gas, and it's getting dispersed. From the slime mold density estimator, we can say how much dispersion should happen in this particular sightline. And if we compute that, we get about 25 to 35% of the dispersion measure must come from the diffuse gas in the cosmic web, which is great. So if you add up all the numbers, I guess I previously said 33%, but there is an uncertainty associated with it. So it's about 25 to 33 or 35% from the Milky Way. So yeah, so about 30% from the Milky Way, 5 to 8% from galactic halos between us and the Milky Way, us and the FRB, about 33% from the FRB host itself, and about 30% from the cosmic web. So if you add all these numbers together, you get something close to 100. Of course, there's a whole lot of uncertainty associated with each of these numbers, so you might not get exactly 100, of course. But this is a proof of concept. It shows us that FRBs are indeed able to detect the cosmic web filament, and this gives us one way of directly inferring the presence of ionized gas that we can't really detect by any other means. So what are the implications of this analysis? So firstly, yes, like I said, FRBs can truly shed light on all invisible matter. It can show us where exactly ionized gas exists, or how much of it exists, although it can't, it can't really show where exactly it exists yet. So the careful analysis of DM budget, the DM budget can be used to infer the presence of matter in dense clusters of galaxies. So this is a possible application for FRBs. So let's say between us and the FRB, there was some sort of galaxy cluster, and we didn't really know how much gas existed in the intercluster medium. So if we were to perform this analysis and account for all the gas found in other reservoirs, then we can say, there's a deficit in the DM and the dispersion measure, and that must come from the intercluster medium. So we can then say, that's how much matter exists in the ICM. if we had thousands of FRBs all in the same field, then we would probably able to perform some sort of dispersion measure based tomography because you get a whole lot of information about various sight lines. And so we should be able to reconstruct without the use of, without using galaxies, how much the cosmic web. So instead of using the Monte Carlo Fizerum machine, we can probably use basically just FRBs to infer the map, the 3D web, the cosmic web structure. FRBs can also be used as independent measurements of the expansion and evolution of the universe. What this means is, I previously said that people performed experiments on the cosmic web microwave background, or they analyzed the data from the CMB, and they were able to infer cosmological parameters like how much matter exists, how much radiation exists in the universe, and all of that. FRBs can probably be used to constrain some of those parameters, given that there are enough of them and all of them are localized. So that's a cool thing about FRBs. So with this, I come to the end of my talk. And if there's one key takeaway that I'd like you to have tonight, it is that FRBs can be used to infer the presence of ionized matter, and that is completely invisible to other methods. So I thank you all again for being patient and listening to me, and I'd be really happy to take any questions at this point.
Well, I've got a question. This might be a little bit off topic, but I'm just I've been following the news about these constellations of satellites that SpaceX and other companies are launching for broadband internet from low Earth orbit. And there's been a fair bit of news about how that's going to impact optical astronomy, like the Vera Rubin telescope, the Large Synoptic Survey Telescope.
Right.
How's it going to affect radio astronomy? These are pretty weak signals that you're getting from 1.5 billion light years away. Are they going to be completely obscured by people downloading kitten videos?
That is a really good question. In fact, well, radio astronomy is already affected by the whole smog of radio waves that we produce right here on Earth, because mobile antennae, spark plugs in cars, in petrol engines, all of these produce radio waves. And the thing about these RFI, or radio frequency interference, is that they can be sort of filtered out because they are only bright in certain frequencies. So radio observations are performed on a broadband in a broad range of frequencies, and we would just lose out these particular frequencies. It's kind of sad, but that's what we have to live with. Unless, of course, we can place a radio telescope on the far side of the moon. That would be nice.
Thank you.
Yeah, no worries.
So I want to just recap on the physics of this investigation you're doing about the speed of light in material. So you're indicating that the photons of different frequencies, which you are detecting in the form of radio waves, but when they're in different frequencies, they are slowed down slightly at different amounts, depending on their frequency. Is that what you're saying?
That is correct.
Okay. So that's how you're able to detect the amount of material that is
Mhm.
going through by
Yes,
the difference of when they arrive here.
that is exactly right. Yes. Yeah. Like pulsars also show this, like I mentioned, but they only show it. Their dispersion is much lower than FRBs, and since they're galactic, they only trace out ionized matter in the galaxy. So from FRBs, we can say a lot more about the cosmology, the cosmic web.
Is this related to the dark matter that you spoke about to begin with, or is this related to the 5%? What is it? Other kind of matter, regular
The
matter.
baryons, yes.
Mhm.
Yes, well, so the dark matter, you can think of the dark matter as some sort of a entity that produces a skeleton for regular matter to reside in, right? The filaments of dark matter are what guide structure formation for regular matter. So the galaxies will trace out these dark matter filaments. So and also the diffuse gas. So all the filaments of diffuse gas that I'm talking about are essentially dark matter filaments with seasoned with regular matter.
Thank you.
Yeah.
I have two quick questions. First off, that was a great talk, Sunil.
Thank you.
And I'm used to thinking of dispersion in terms of lens properties and, positive dispersion and kind of negative or anomalous dispersion being used to correct and make achromatic doublets and things like that. Is there any possibility that there are sources of anomalous dispersion out there that are not being taken into account, for one thing? And then the second is, I liked your slime mold model, your Monte Carlo model of the filaments. Is there it seems like that is the dispersion that you're getting from the FRBs is the constraint on that model, right? That's kind of giving you an estimate of the amount of matter that's there. Is there a separate or orthogonal way to get an estimate of that as well, just to kind of double check?
Well, okay, let me try to answer the second question first, because that's slightly easier, I think. So the dispersion measure itself is not being fed into the model, and what we're estimating is completely from the optical data from SDSS. So the 33% dispersion measure, that is an independent estimate. So we are using this model, we're essentially testing this model against the dispersion measure of the FRB.
Oh, that's cool. So it's independent. That's very cool.
Yes. As for the first question, I'm not exactly sure what you would mean by anomalous in this context. So maybe you could
Well, it's a crazy question. I was wondering if there's any material that you can imagine that would actually have the opposite effect on the dispersion as the ionized gas passing through, something that's kind of compensatory. It probably there is.
I see.
It's just I just wondered if there's even a possibility of that.
Right. Yeah. So far, as far as our current understanding of material science is concerned, we don't think there's that sort of thing. So I guess in achromatic lenses, the way you correct for dispersion is that you have something dispersing in the opposite direction, and that you achieve sheerly by geometry. There's no such geometry in play over here because it's just one beam of light coming towards you. So whatever is getting dispersed is completely along this beam. There's no way you can have anomalous dispersion and like something canceling it out. Yes.
I was curious to ask about I think you said there was intergalactic plasma. What what composes that? What kind of elements? I was wondering.
That's a good question. So plasma in the universe is mostly hydrogen and helium. It's similar to that of the sun. I guess yeah, it's slightly different in the sense that there's a whole lot less other elements present. So astronomers like to call them metals. So anything that is more massive than helium is called a metal in astronomy. And there are not all that many metals in this gas, but it's mostly, I think it's about, I forget the exact numbers, but I think it's 70-30 ratio for hydrogen to helium. That's what it's mostly made of.
I'm looking at my periodic table right now. Thank you.
Aha, okay. Yeah, and it's mostly ionized, so it's not even hydrogen and helium, it's a bunch of protons and helium nuclei and electrons. And the dominant contribution to the dispersion measure comes from the electrons themselves, so yeah.
And when I think of plasma, I usually think of something hot, but perhaps if it's out there in deep space, could it be that it's under such low pressure that it can be a plasma without having a high temperature? Or does it actually have a high temperature?
So we can estimate or assign a temperature to this plasma, and it's actually really high. It's about 10 million Kelvin. So it is hot, and that's why it's called warm hot intergalactic medium. But yeah, it's also very diffuse. So yeah, it could probably you might be right in some sense.
Thank you. That's very interesting. I've been reading about that in a Star Wars novel.
Oh yeah.
And I always wonder like how much the author is drawing on, science versus fiction.
Right. Yeah. Yeah. There is plasma, but it's like very diffuse. If to give you a sense of density, it's like diffuse plasma is usually like having one particle in 100,000 cubic centimeters of space. So it's that diffuse. So yeah, it's very, very sparse, better than the best vacuum that we have on Earth.
Two questions. In regards to the plasma being very hot, so if this is intergalactic space, where would the heat source be? And then the other one is in regards to the dispersion measurement. Even though it's maybe one hydrogen atom per was it 100 kcc of space, that the idea is because the radio waves are going through so far to get to us, that it is the equivalent of dense plasma. Is that what I'm hearing?
Yes, sort of. Yes. Yeah, it's simply because it's traveling through a whole lot of plasma. Can you repeat your first question though?
Oh yeah, since you mentioned in regards to the plasma being hot, but if this is intergalactic space, what would the heat source be?
That's a very good question. So the plasma occurs because it's getting photoionized. So there's background radiation, UV radiation from stars and active galactic nuclei in the universe, and these photons are energetic enough to kick electrons out of orbit and thus produce this plasma. So back in the early days when the universe was still pretty young, everything was neutral, and because there were hardly any stars. But eventually stars started forming and they started producing bubbles of ionized gas until like there was so much ionizing radiation that everything got ionized between us. So everything is, everything is visible in the universe thanks to stuff being ionized. If everything were neutral, then it would be fully opaque. We wouldn't be able to see anything.
Okay, thanks.
So I can add one more question about the heat. So the high temperature is simply an indicator of the speed that these particles are moving. Is that right?
Yes, you can think of it as a statistical speed. Yes, higher the temperature, the higher the average speed of particles.
So,
Okay,
is it, sorry, one more question.
yes.
So those filaments in the cosmic web, so from my understanding, is it correct to say that most of those filaments are comprised of dark matter and just peppered with a little bit of baryonic matter, mostly plasma? Is that accurate?
Yes.
Or, okay.
Yes, that is correct. Yes. So yeah, according to the CMB, about I forget, 25 to 5. So there's like 5 times more dark matter than regular matter. Yeah.
I see. Okay. And how do we know? So I know you talked about the that estimation, the density estimation technique with the fungus example. How do we know that that model is accurate?
Oh, right. Good question. The way we make sure that it is accurate is that we calibrate it against a cosmological simulation. So we just don't take the density. We first estimate the slime mold trace density, and then we take a cosmological simulation with the same galaxies, and we ask, okay, what is the exact dark matter filamentary density, and then we perform a one-to-one mapping. So that's how we're able to say, oh, this the slime mold density corresponds to this physical overdensity of dark matter.
Got it. Okay. Thank you.
Yep. Okay, so I guess if there are no further questions, I'll stop sharing. Thanks for being a wonderful audience.
It was a good talk. Thank you.
Very, very good. And the slides were
having
good, very helpful.
Great. Glad you enjoyed them.
Thanks.
And it will be recorded into SFAA's archives. So I've been scribbling notes as fast as I can, but I'll be happy to see it again.
Sure. Yes.
Yeah.
Well, thank you all for an excellent presentation, and Sunil and Linda for finding great speakers.
Oh, I'm so pleased. Thank you very, very much.
Hopefully I'll be with you next month.
Good.
Okay, bye-bye.
Bye-bye.
See y'all. Good night.